Now we say it's the movement of the atmosphere that forces the movement of surface waters. The movement of one fluid, in this case air, the atmosphere, against another fluid, in this instance water, whether it's seawater or fresh water. The result is drag, a fluid drag or friction, which is known as wind stress. This wind stress on the surface pushes the water at the surface before it as a wind drift current. So again, we've seen this before a few minutes ago. The wind is blowing on this water. It's grabbing onto it like Velcro, and it's dragging it along with it. So the wind grabs the water and takes it for a ride at the surface. However, we have this Coriolis effect jumping into the game again. And this Coriolis effect, just like in the atmosphere, is going to deflect water to the right. So the wind is going to be deflected by the Coriolis effect. The water is also going to be affected by the Coriolis effect. In this case, we have a bit of an additional twist, such that when the wind blows on water, the Coriolis effect results in a current that's generally about 20 to 25 degrees to the right from the direction of the wind. Ultimately, this results in the large semicircular gyres that we see in each large ocean basin. So here, in a very simple schematic, we have a gyre. We'll say it's the North Atlantic. We have the trade winds here blowing to the west. They're going to force this water to the west. It's going to curve to the right because of the Coriolis effect. It then gets entrained in the westerlies at the mid-latitudes. They're going to force it to the east, but as they force it to the east, they're also deflecting it to the right. So the net result is, no matter where you are in this gyre, the wind is going to force the water along with it, but deflect it to the right because of the Coriolis effect. The net result is we have water piling up in the center here of these gyres. The water is piling up in the center of these gyres because of the Coriolis effect. Again, no matter which portion of this gyre you're in, the water gets deflected towards the center of the gyre. And by piling water up here in the center, we essentially make the sea level higher at this point. Now, because sea level is higher at this point, it wants to level out. It wants to flatten. So it downwells, or it subsides in this location. So we have a wind that is causing a gyre. This gyre is going to be influenced by the Coriolis effect, producing a bulge in the surface water here that then descends into deeper water. So wind at the surface in this case is generating downwelling, producing a deeper water current. Kind of cool and totally unexpected. So ultimately we end up with a real world surface current map like this that looks similar to that simple model we saw a minute ago. Now we have to think about additional complications when we go into deeper water. So if the oceans were all the same depth, if all of this water that you see in the map here was the same depth, life would be a lot easier for an ocean modeler or an ocean circulation modeler. But there are things in the way. When you go down into the ocean, it doesn't look the same as it does from a satellite image like this. One of the things we need to consider is what's known as the Ekman spiral. This Ekman spiral generates what's known as Ekman transport of water. This Ekman transport dictates that water is going to move at a 90-degree angle relative to the wind that forces the water's motion. What the heck does that mean? Here we have a wind current. It's blowing steady in this direction. The surface current, the water right at the surface, is going to be deflected by 20 to 25 degrees usually. If you go a little bit deeper, 20 to 45 degrees as depicted here. Nonetheless, the wind is blowing in one direction. It's forcing the water, but that water is influenced by the Coriolis effect, so it doesn't travel in the same direction as the wind. It's to the right. If we go a little bit deeper, the water in that portion of the water column is deflected to the right from this water. A little further, deflected to the right, deflected to the right. At this point, deflected to the right. The water is moving at a 90-degree angle relative to the wind at the surface. This is the bulk of the water, so we would say this deep water current is at a 90-degree angle relative to the surface wind. So that's something we didn't consider, that the wind blows in one direction, the water blows at a 90-degree angle relative to that wind because of the Ekman spiral. But now you know. So ultimately, this convergence in the center of this subtropical gyre that's forced by the Coriolis effect and Ekman transport, again, is going to lead to a convergent bulge in the ocean. This convergent bulge means the surface layer is thicker. Again, this wants to level itself out. By leveling itself out, it's got to force water downward. You can't go up. You can't go this way or this way because the Coriolis effect is forcing it towards this bulge, no matter which direction it's traveling. Okay, so we're generating a downwelling zone here in the middle of a gyre. In areas where there's divergence, where surface waters are moving away from one another, we have a divot in the surface layer. It's thinned out. The ocean strives to equalize by bringing water up from the depths. This upwelling turns out to be very important for bringing nutrients from deep water. Basically, biological productivity at the surface captures nutrients mixed with organic matter that's generated by photosynthesis. That blob of organic matter and nutrients sinks to the bottom, where it's broken down by bacteria and a number of other things, freeing up those nutrients. Those nutrients sweep around the world in deep waters until there's an upwelling. And when that water upwells, it brings all those nutrients to the surface, it fertilizes the surface water, and we have biological activity, extreme biological activity. So let's throw in some additional complications here. The pressure gradient force is going to come into play here. It's going to fight the Coriolis effect to influence the ultimate ocean circulation. So again, here we have the example of westerly winds flowing in this direction, west to east. There's an offset between the ocean surface current and that wind caused by the Coriolis effect. Ultimately, that's going to continue as we work around the gyre, forcing water to pile up in the center. Now, as this water piles up in the center, we're going to see a component of the pressure gradient force, a component of the Coriolis effect. When they're equalized, we have the resultant water flow. Now, in the atmosphere, this would be the jet stream. In the ocean, we would call this a geostrophic current. So it's geostrophic flow, a geostrophic current. It's really similar to what we see in the atmosphere in a jet stream. And the result is we have a geostrophic current that flows approximately perpendicular to the slope of the sea surface around a gyre. So we have a high point here. We have water wishing to slide off of this high point. It's going to be forced by the Coriolis effect in this direction, and that's going to continue all the way around the gyre. So it perpetuates this gyre. Now, the gyre is going to have a different strength depending on where you are latitudinally. At the North Pole, we have a very large vorticity. At the equator, zero vorticity. Now, you've probably seen some hokey videos on YouTube about people standing eggs on end at the equator and toilets that don't flow in any particular direction at the equator. All that's made up. Your toilet flow, the direction of the whirlpool in the toilet as it's being flushed is dictated by the shape of the toilet more than the Coriolis effect. The Simpsons, they didn't disprove that. Okay, so as we go higher and higher in latitude, we see an increase in vorticity. That's going to be an increase in the intensity of the Coriolis effect. What this results in is what's known as a western boundary current. These western boundary currents tend to be narrow and fast because of this vorticity effect. So again, here we use the North Atlantic because that's what most of us are most familiar with. The western continent would be North America. The eastern continent would be Europe and North Africa. The net result is we have this big gyre rotating in the North Atlantic. As it approaches the continent of North America, it's going to increase in latitude. This increase in latitude increases the vorticity, and the result is, as we travel along this gyre, it speeds up. So slow, fast, slow, very slow, getting slower because it's heading to the south where there's less vorticity, Heading west, no change in vorticity. Heading north, speeds up. Sorry, went off the track there. And slows down again, speeds up, slows down, speeds up, slows down. And this continues as long as these continents maintain this position. You could think of this as ice skaters. They change their vorticity by changing the spacing of their arms, the distribution of their weight above their center point. So when skaters are rotating with their arms out, they tend to rotate slowly. When they tuck themselves in, their rotation speeds up. The best example of this, or the best known example, is the Gulf Stream. So this Gulf Stream was discovered by famous wine drinker, first post office general of the United States, scientist, general party boy, very important in the early history of the United States, Benjamin Franklin. He's credited with saying, "Wine is proof that God loves us and wants us to be happy." I don't know if he actually said that. It's also been described as beer is proof, but that's definitely made up. What did Franklin do in his spare time? He looked at the postal records of mail ships traveling from Europe to the United States, or the colonies at the time. He noticed that when ships went to certain locations, like, say, South Carolina, they sometimes took a lot longer than expected to get there. So to get from Europe to here, somewhere in South Carolina, and when they returned, they got there fast. They got there a lot faster than normal. When ships travel to New York, which is located about here, or Boston up here, he didn't see this influence, this getting to North America too slow and getting back to Europe too fast. So he thought maybe there's a current involved. Turns out he was right. When ships are traveling on this route, they're fighting against this Gulf Stream. It's traveling at a couple miles an hour, or a number of kilometers an hour. And if you're traveling against it, just like an airplane going against the jet stream, you have to expend more fuel. In this case, they're sailing ships, so not more fuel, but more days. On the other hand, if you catch this stream heading back east, you're going to speed up by the amount of movement in the current plus the wind that's driving this current. So you can get back to Europe. You can return mail from South Carolina to London much faster than you can get London mail delivered to South Carolina. Now, when we look at depth, we have a bit of a different story. So here we have the high vorticity western boundary current, the Gulf Stream, that runs from the surface to a pretty considerable depth of about 2 kilometers or so. Whereas over here in the east, the Canary Current running along West Africa is a broad, shallow, weak current. And that's the difference in vorticity that we were talking about a minute ago. So fast-moving water here on the western boundary, slow-moving water here on the eastern boundary. Brings us to La Nina and El Nino. We talked about this a little bit in the atmospheric circulation component of the course, and it's illustrated schematically here, such that during La Nina, the little girl, what that means, the strong easterly winds are going to drag warm water to the west. So the trade winds are moving to the south. They're going to grab this surface water, the Pacific, drag it to the west, where it's going to surround eastern Australia and intersperse here between New Guinea and the Borneo, the Indonesian islands. This results in upwelling. Cold water full of nutrients is going to rise up and replace this warm water that's being pushed to the west. Now this flip-flops to El Nino, which is the little boy. In this case, it refers to Jesus, the little Christ child, because it often occurs around Christmas time. In this instance, trade winds reverse direction, and the warm water gets pulled back to the east. When this warm water piles up off the coast of South America, the upwelling is stopped, and the whole food chain grinds to a halt. There's reduced plankton, there's reduced zooplankton, that reduces the anchovy flocks of fish that reduces the seabirds and reduces the seals and the toothfish, and the whole economy based on fish collapses. Now, this has been known since around 1500 AD, about 500 years we've known about this current, this flip-flopping. We know a lot more about it now than we did 500 years ago, but even 500 years ago, the fishermen from Portugal predominantly noticed that something was happening. They described it.